This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today we're delving into the research paper Scaling Laws for Neural Language Models, a deep dive into the empirical scaling laws governing the performance of large language models. Our focus will be on the practical implications for researchers and developers working with these models. Let's start with the core findings. What are the key scaling relationships identified in the paper?
The paper establishes robust power law relationships between language model performance, measured by cross-entropy loss, model size, number of parameters, dataset size, and the total compute used during training. These relationships hold across several orders of magnitude, revealing a predictable scaling behavior. Crucially, the paper finds that performance is strongly influenced by the overall scale of these three factors, while the impact of architectural details like network depth or width is relatively minor within a wide range.
That's a significant finding, suggesting a focus on scale over the intricate architectural tuning. Can you elaborate on the specific power law exponents and their implications for resource allocation?
The paper provides specific power law exponents for each factor. For instance, the loss scales as a power law with model size, n, dataset size, d, and optimally allocated compute, c min. These exponents dictate how much improvement we can expect from increasing each factor. For example, doubling the model size doesn't necessarily have the loss. The actual reduction is determined by the exponent. Understanding these exponents is critical for efficiently allocating resources, as it guides the optimal balance between model size, data, and compute.
The paper mentions optimal allocation of compute budget. How does this concept translate into practical training strategies? What are the implications for training large models?
The optimal allocation suggests that, given a fixed compute budget, the most efficient approach is to train very large models on a relatively modest amount of data and stop training significantly before convergence. This counterintuitive finding highlights the sample efficiency of larger models. They reach a given performance level with fewer optimization steps and less data than smaller models trained to convergence. This has significant implications for reducing training time and computational costs.
The paper also addresses overfitting. How does the scaling law help manage this challenge when scaling up model and dataset size?
The paper presents a combined scaling law that accounts for both model size, n, and dataset size, d, effectively capturing the interplay between model capacity and data availability. This law predicts the extent of overfitting based on the ratio n sig 0.74 sig d. This means that to avoid overfitting when increasing model size, n, by a factor of 8, we only need to increase the dataset size, d, by approximately a factor of 5. This sublinear relationship is crucial for efficient scaling.
The paper introduces the concept of a critical batch size. How does this factor into the overall scaling laws and optimal training strategies?
The critical batch size, bcrit, represents the optimal balance between training speed and compute efficiency. The paper shows that bcrit is primarily determined by the achieved loss, not the model size. Training at or near bcrit minimizes the number of training steps while efficiently utilizing compute resources. This is important because it affects the overall compute required, c, and the number of steps, s, needed to reach a target loss.
The paper concludes with a discussion of potential contradictions and limitations of the scaling laws. What are some of these limitations, and what are the implications for future research?
The paper acknowledges that the observed power law relationships cannot hold indefinitely. At some point, performance must saturate as the model approaches the theoretical limit of zero loss. The paper identifies a potential contradiction between the scaling laws for compute-efficient training and dataset size limitations. This suggests a potential upper bound on model size and compute beyond which the current scaling laws may break down. This highlights the need for further research to refine the scaling laws and understand their limitations. Further investigation into the theoretical underpinnings of these empirical observations is also crucial.
The paper also touches upon the generalization capabilities of these models. How does model size affect generalization performance?
The study shows that generalization to unseen data distributions improves smoothly with model size, almost exclusively depending on the in-distribution validation loss. This suggests that larger models not only perform better on the training data, but also generalize better to new data, indicating a strong correlation between training performance and generalization ability.
The paper compares transformers to LSTMs and universal transformers. What were the key differences observed in scaling behavior?
The comparison reveals that transformers significantly outperform LSTMs, particularly for longer contexts. LSTMs plateau in performance after processing a relatively small number of tokens, while transformers continue to improve as they process the entire context. Universal transformers, which reuse parameters, show slightly better performance per parameter, but slightly worse performance per flop compared to standard transformers.
The paper suggests that the scaling laws might be applicable to other generative modeling tasks. What are some potential areas for future research based on these findings?
Extending these scaling laws to other domains like image, audio, and video processing is a natural next step. Investigating whether these relationships hold for different model architectures and training methodologies is also crucial. Furthermore, developing a theoretical framework to explain the observed power law relationships would provide a deeper understanding of the underlying mechanisms driving these scaling behaviors.
Finally, what are the broader implications of these findings for the field of large language model development?
The findings strongly suggest that larger models, trained efficiently, will continue to yield significant performance improvements and enhanced sample efficiency. This shifts the focus towards scaling up model size as a primary driver of progress, rather than solely relying on massive datasets. This also highlights the importance of further research into efficient training techniques and model parallelism to fully leverage the potential of these increasingly large models. The research emphasized the need for a deeper theoretical understanding of the observed scaling laws to guide future development and optimization efforts.
This has been a very insightful discussion. Thank you for sharing your expertise.